Hello everyone, I am Shankha Subra Sanyal and I welcome you all on behalf of S-Cube's classes. Well, I'm really thankful to all of you for your overwhelming response. The amount of love that you have shown through your mails, through your feedbacks, I'm really grateful. I'm really privileged. Well, in our previous discussion on number system, we have studied about real numbers, especially about irrational numbers. In this lecture, we shall continue our discussion on real numbers. We begin with two important results, namely Euclid's division lemma and the fundamental theorem of arithmetic. Now, what is a lemma? A lemma is a proven statement used for proving another statement. Let's take an example. When you people were in your junior classes, we had taught you as teachers how to find the HCF of two numbers by a method called long division method. Now, this long division algorithm is absolutely based on Euclid's division lemma. So what is Euclid's division lemma? It is actually for any two given positive integers a and b, there exists unique whole numbers q and r such that a can be represented as bq plus r, where r lies between 0 and b. Here we call a as dividend, b as divisor, q as quotient, and r as remainder. So if you just think, how can a dividend be represented? We can represent a dividend by multiplying the divisor with the quotient and add the remainder to this. Let's take an example to understand this a little better. Suppose we divide 117 by 14. So what are we going to do? When I multiply 14 with 8, I get 112. Now, if I subtract that from 117, I get a remainder 5. So very simply, we get the divisor to be 14, the quotient to be 8, and the remainder to be 5. So the dividend 117 can be represented with 14 into 8 plus 5. Isn't that what takes us back to the formula? Dividend is equal to divisor into quotient plus remainder. Is that easy? If that's so, let's check out with another number. A number when divided by 73 gives 34 as quotient and 23 as remainder, and you are asked to find the number. So if you look around with this question, here all the quantities that is to be found out, like the divisor, quotient, and remainder is given to you. You had been asked to find the dividend. That means the number has to be found out. So what I do, I have the formula dividend is equal to divisor into quotient plus remainder. So I multiply 73 with 34, add 23 to that, and my number is 2505. So the number that we were actually looking out for is 2505. I just now uttered a word called algorithm. So what is an algorithm? An algorithm is a series of well-defined steps which gives a method for solving a certain type of problem. Finding the HCF of two given numbers by Euclid's division algorithm. What we are supposed to do over here? It is a technique to compute the HCF of two given positive integers, say a and b, with a greater than b. And the steps that we are going to follow is as written on the screen. First, on dividing a by b, we get the quotient q and remainder r, such that a equal to bq plus r, where r lies between 0 and b. This is the first step. Second, if r is 0, then HCF of a and b is b This is written as HCF bracket A comma B bracket close. If R is not equal to 0, then apply the division lemma to B and R. We go on continuing this process till the remainder is 0. The last divisor will be the required HCF. We must note that this method is also known as successive division method. Let's take an example. Let us use Euclid's division algorithm to find the HCF of the numbers 867 and 255. By the way, this question came in 2018 compartmental exam. What we are supposed to do over here, we are asked to find the HCF of 867 and 255 by using the steps that has been discussed. What we are finding over here, we find that 867 is more than 255. What do that mean? That we divide 867 by 255 and we get 3 as the quotient and 102 as the remainder. Now, what was said? If there is a remainder, then we go on successive division method. So again over here, this can be represented as 867 is nothing but 255 into 3 plus 102. Since 102 is not equal to 0, we again go for the division. What we do? We divide 255, which was the previous divisor, by 102. And what do we get over here? We get 51 as the remainder. We again repeat the steps. And what do we get? We get 0 as the remainder. Since we get 0 as the remainder, that means 51 happens to be my required HCF. Since the remainder is 0, our procedure stops over here, right? Let's take another example. Suppose you are asked to find the HCF of 1651 and 2032, and we need to express it in the form as given on the screen. 1651 m plus 2032 n, where m and n are some integers. Again, this question is a very important question. Please focus. Over here, we find 2032 is greater than 1651. So we go on the long division method. What I do? I find that 1651, if it is multiplied with 1, we are left with 381 as the remainder. We go on doing the process. And what we find? We find that 2032 can be represented as 1651 into 1 plus 381. Again, 381 being not equal to 0, we repeat it. And what we find? 381 into 4 plus 127, which was the remainder, is equivalent to my 1651, what I started off with. Since again the remainder is 127, I cannot stop over here. I again need to carry another step. And what do we find? That thrice 127 will give me a remainder 0. That means what? This actually stops my calculation because I have now got a remainder 0, means 127 happens to be my HCF. So the remainder is 0, and the HCF between 1651 and 2032, these two numbers, is 127. The second question that we got over there, the second equation rather, it's 1651 is nothing but 381 into 4 plus 127. Now check 381 into 4 plus 127. But how did I get 127? It can be represented as 1651 minus 381 into 4. Check on with the previous step. So what do I find? I find that 1651 minus, check with 381. How can I write 381? 381 was the first step that we got. Over there it was 2032 minus 651, and then the 4 already exists. So I can write 1651 minus 2032 minus 1651 into 4. If I open up the bracket, I get 1651 into 5 plus 2032 into minus 4. If you remember, we were asked to represent the HCF, which is 127, in the form of the numbers 1651 and 2032. So if I go around with this, what do I find? I find it is 1651 into m plus 2032 into n, where m is nothing but 5 and n is nothing but -4. Let us take another example. Show that every positive even integer is of the form 2m and that every positive odd integer is of the form 2m plus 1, where m is some positive integer. Well, let n be any arbitrary positive integer. So, on dividing n by 2, let m be the quotient and r be the remainder. So what are the two possible cases that might arise? We might get 2m plus r, where the remainder can be 0, it can be 1, or it cannot be 2 because we are dividing it by 2. So the only possible cases is 0 and 1. So this can be represented as n is equal to 2m plus 0 doesn't make any sense, and 2m plus 1 for any positive integer m. So when n is equal to 2m, in this case it is clearly a case of even number, while if n is equal to 2m plus 1, again this is clearly a case of odd number. Thus the number that is given to us n, or for that reason every positive even integer, is of the form 2m, and every positive odd integer is of the form 2m plus 1 for some positive integer m. Suppose you are given a question to show that any positive integer is of the form 3q or 3q plus 1 or 3q plus 2 for some integer q. Check over here, it is written 3q. That means my range over here for r will be from 0 to 3. I mean, it will be less than 3. Why it is less than 3? Because if it is 3, then again the remainder becomes 0. That means my range will be 1 less than the number that is given to us. So on dividing n by 3, quotient is q, remainder is r, then we can represent this as n is equal to 3q plus r, where r ranges between, the remainder ranges between 0 to 3, 0 to rather 2, less than 3 means 2. So n is equal to either 3q if the remainder is 0. If the remainder is 1, then I can write it as 3q plus 1. If the remainder is 2, I can write it as 3q plus 2. Again, I repeat, the remainder cannot be 3 because we are dividing it by 3. If it is 3, then the remainder will become 0. So any positive integer is of the form 3q or 3q plus 1 or 3q plus 2 for some integer q. Let's extend our discussion and take another example. If you are asked to show that every positive odd integer is of the form 4q plus 1 or 4q plus 3, mark my words, odd integer, right? 4q plus 1 or 4q plus 3 for some integer q. We apply the same procedure once again. See, over here it is 4q plus 1. If it is 4q plus 1, that means your remainders can be 0, 1, 2 and 3. I repeat, the remainders can be 0, 1, 2 and 3. It cannot be 4. So the range of remainder will be from 0 to less than 4, that is still 3. If I represent this number as n is equal to 4q plus r, then if the remainder is 0, we'll get 4q. If the remainder is 1, we'll get 4q plus 1. Similarly, we'll get 4q plus 2 and 4q plus 3. Now clearly 4q and 4q plus 2 are even since n is odd. So we have n not equal to 4q and n not equal to 4q plus 2. We discard these two. So what are we left with? We are left with two of the remaining cases, 4q plus 1 and 4q plus 3 for some integer q. Hence, any positive odd integer is of the form 4q plus 1 or 4q plus 3 for some integer q. If the same question would have been given for even integer, I would have taken 4q and 4q plus 2, right? Let us try out few more questions. Let us find, using Euclid's division lemma, the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Well, this came in 2008's board exam. Let n be any positive integer, the same way we begin. So this can be represented as n is equal to 3q plus r, where q happens to be my quotient and r my remainder. Since it is 3, so the remainder can be what? 1 less than 3, that is 0, 1 and 2. So I have three cases over here. 1, remainder 0. Second case, remainder is 1. And the third case, remainder is 2. Let us try out with all these three cases. Since the question asks us to find the square of any positive integer, what I do, I basically square this number. I have taken n, which is equal to 3q plus r. So this can be represented as n square. Now, if I square the term on the right hand side, a plus b whole square formula, it would turn into 9q square plus r square plus 6qr. Let us put the values over there. When r is 0, what do we have? We have n square is equal to 9q square, which can again be represented in terms of 3 into 3q square. Why do I do it 3 into 3q square? The reason is the question asked me to find find the answer in terms of 3m. So over here, what I do, I represent 3q square as m, right? If I have remainder as 1, then this same equation would turn into 9q square plus 1 plus 6q, which can again be represented in the form as shown on the screen. I would always try to represent things in the form which will be having 3 as a multiple. So I get 3 into 3q square plus 2q plus 1. Now this entire thing, 3q square plus 2q, can be taken as m over here, which is again represented as an integer. So this case will give me 3m plus 1. If I move on to the third case, over here we take r equal to 2. So putting the value of r equal to 2 in n square, we get 9q square plus 4 plus 12q. I repeat, again I'll be trying to put this in the form 3m plus 1. So for that, I'll take a multiple of 3. Now 4 cannot be represented as a multiple of 3. So what do? I make it 3 plus 1. So it becomes 3 into 3q square plus 4q plus 1 plus 1. This entire term 3q square plus 4q plus 1 is taken as m, which is an integer. Thus we see from the last three cases that we have discussed that the square of any positive integer is of the form 3m, or it is 3m plus 1, where m is an integer. We have a similar question as the last one over here. Here we need to show that the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8, whereas m is some integer. We begin in the same fashion as we had been doing. So what I do, I take and represent this as n is equal to 3q plus 1, where n is any arbitrary positive integer, and q and r are quotient and remainders respectively. Since it is 3q plus r, so now the value of r can range between what? 0 to 2. That is 0, 1 and 2. It cannot exceed 2, right? Let us take a cube of this. So n cube is nothing but 3 plus r whole cube. We put it into the formula of a plus b whole cube. And what do I find? I get it to be 27q cube plus r cube plus 9qr 3q plus r. On opening the brackets and rearranging the terms, we get something which is written on the screen. Now, if I put r to be 0, what do I find? We find n cube is nothing but 27q cube. Now check. Over here, I need to represent it in the form of 9m or 9m plus 1 or 9m plus 8. So 27q cube can be written as 9 into 3q cube, where m represents 3q cube. So we get it is nothing but n cube is equal to 9m. Let's go to the next case. Here the remainder can be 1. If the remainder is 1, in that case the equation would look something like this: 27q cube plus 27q square plus 9q plus 1. Again over here we do the same trick. I represent this in the form what? In the form of 9, in a multiple of 9. So 9, if I take out 9 from all these, I'm left with 9q, 3q square plus 3q plus 1. Now this m will be representing nothing but q into 3q square plus 3q plus 1. So now this number can be represented n cube as 9m plus 1. The last case that we have is r equals to 2. If I put that value, again I get, after rearranging the terms, I would get it to be 9m plus 8, where m is nothing but q into 3q square plus 6q plus 4, which is again an integer. Hence, the cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8 for some integer m. Let us take this last type of problem. It says, show that 1 and only 1 out of n plus 1 and n plus 2 is divisible by 3, where n is any positive integer. Now, if you check, since it is divisible by 3, so what would be the remainders? I said it should be 1 less. That means 3 minus 1 is 2. So the remainders can be 0, it can be 1, it can be 2. So when we divide n by 3, it can be represented as n is equal to 3q plus r. And the remainders can range between 0, 1 and 2, where r and q are remainder and quotient respectively. So what are the cases? I can have remainder to be 0, I can have remainder to be 1, I can have remainder to be 2. So there are 3 cases which arise out of this. So n can be 3q, n can also be 3q plus 1, n can also be 3q plus 2. Now clearly, if it is n is equal to 3q, it is divisible by 3. If n is equal to 3q plus 1, then n plus 2 is what? 3q plus 3, or if I take 3 common out of it, I would be getting 3 into q plus 1. Again, since there is a multiplying factor 3, that means it must be divisible by 3. Last case, we have n plus 2. What we do over here? N is equal to 3q plus 2. So if it is 3q plus 2, we have n plus 1. So n plus 1 means 3q plus 2 plus 1. That means 3q plus 3. So we can take 3 out of that and make it common. So we have again a multiplying factor 3. So clearly it is again divisible by 3. So in this case, n plus 1 is divisible by 3. Thus, we can conclude that 1 and only 1 out of n plus 1 and n plus 2 is divisible by 3. Because if n plus 1, n plus 2, all 3 are divisible, not possible. So only one of this is possible, that it is divisible by 3. So this brings us to the end of the lecture. Well, before I sign off, as I always do, I would request you, in case you have any queries, please do feel free to write to me at scubesclasses@gmail.com, or you can WhatsApp me on the numbers given on your screen. It would be a privilege on my part to be addressing your queries. Thank you so much.